In this lesson, we're going to look at how we can actually solve some applications of calculus. In particular, the idea of optimizing a model. The whole idea of calculus is to find optimal things, the highest, the lowest, the max, the min, and all those ideas. And in general, for now, we're going to deal with polynomial functions, but also any other function. Okay? The big key ideas, if you want to find a maximum or a minimum, they always occur where your derivative is a flat line, where your rate of change is 0. Think about a ball going up and then coming back down. Just at the top, it stops for a second, the point where our derivative equals 0. Okay? And your function may have more than one of these things. You may have 3, as this one does. We can find those by solving the equation where your derivative is set equal to 0. So we're going to go back to grade 10 for a second, if you will, and look at some quadratics. Those are sort of our more common situations that we've dealt with for years and years. And then we'll try and do some more advanced functions after that. So look at the height of a daffodil above the ground given by this quadratic, where W is the time in weeks after the plant has broken through the surface. And we want to find the height of the daffodil after 2 weeks. I want to find a point, in other words. I want to find what H at 2 is. Okay, so I can just use my equation. 24 times 2 minus 2.4 times 2 squared. Put that all into our calculator, and we should end up with 38.4 centimeters. Okay, and that's your point. Okay. Part B, find the rate of growth. Our instantaneous rate of change, our growth at any point. Let's find the equation for it. So I'm looking at I'm looking at the derivative of h, the height, with respect to the number of weeks that pass by. This is just a power rule question. So we get 24 minus, well, 2 times 2.4 is 4.8, and subtract 1 from your exponent. So my height, thinking about this, is given by 24 minus 4.8w. It's a nice straight line. It's going to grow and grow and grow. But the growth rate is actually slowing down because it's a negative. And eventually it's going to stop. Your flower doesn't grow forever and ever and ever. Part C, when will the daffodil reach its maximum height? And what is that height? So a parabola, in particular a parabola that opens down, that's what our A value is telling us. We're trying to figure out the maximum. Where do maximums happen? Where our rate of change, our derivative, equals 0. So in part C, we're going to take our derivative, we're going to make it equal 0. So 0 equals 24 minus 4.8w. We can solve that nice linear equation. 4.8w equals 24, so w must be 5. After 5 weeks, our flower is going to stop growing. What's the height of that time? Well, let's go back to our initial equation where we find points. Our height is given by 24 times 5 minus 2.4 times 5 squared. If you put that in, you should get 60. Therefore, the max height is 60 centimeters after 5 weeks. And just to point out to you, this is a quadratic, and you can actually use some of the same ideas as quadratics to solve this problem. You might recall axis of symmetry in vertex. X equals negative b over 2a. Here's your b, here's your a. You'd end up with negative 24 over 2 times negative 2.4, which comes out to 5. Hey, that's the same answer we get when we do this. In fact, if you look at the numbers, we're taking 24 and dividing by 2 times 2.4. Okay? That's what the derivative is doing for you. It's doing the negative b over 2a and solving that equation. It's just doing it in a much faster fashion. And it's doing it in a fashion we can use for cubics and quartics and other things that don't have an axis of symmetry. Okay, let's look at another example. From grade 10 again, quadratics. An industrial shed has a total floor space of 600 meters squared, and it's going to be divided into 3 rectangular rooms of equal size. So we need a rectangle, we're going to divide into 3 equal sized things. The walls cost $60 per meter to build. What dimension should the shed have to minimize the cost of the walls? So my shed, which is the entire thing, needs some variables. Let's call this X, and let's call the width Y. What do I know about this shed? I know its area is given by length times width. I know the area is 600, the length is X, and the width is Y. I've got two variables. I'm going to need two equations. So what else do I know? I know the walls cost 60 meters to build. So I know something about the cost. I need to be able to make myself an equation about cost at some point. How can I do that? Well, my cost equals $60 for every wall. What kind of walls do I need? I need to have two X's plus X at the top, right? That way. And I need to have all these Y's. I need 4 Y's. Hey, that's a second equation. To solve two equations at one time, I either have to do elimination or substitution or comparison, and I don't really have this set up for elimination because I don't have numbers on both sides. I have a variable in this equation, and I got variables in the other equation. So I'm actually going to use substitution. In particular, I'm going to get one of my letters by itself from this equation. I'm going to take 600, put it over y, and that's what x is. Or I'm going to take 600 and put it over x, and that's what y is. Doesn't make a difference which one I use. I have an expression for one variable in terms of the other. Either way, I can substitute that into my equation. I'm going to pick the y one. I'm going to take this and stick it in here. What's that going to look like? Well, I still have my costs, $60 per wall. Still got the 2x. I need 4 y's. What's y? Well, it's 600 over x. I can simplify this. 60 times 2x plus 2400. And really it's x to the negative 1. There's a reason I put it that way. Just give me a second, I'll explain it. And really this is my cost in terms of x. Well, this kind of started looking like a function now. I can expand my brackets. 60 times 2 makes 120x. I can also do the next piece, and I get 144,000 x to the negative 1. I've got an expression in terms of the cost with respect to x. What have I been asked for? What are the dimensions that minimize the cost? I get minimums where my derivatives equal 0. Let's figure out where that is. So derivative of 120x is just 120. And for this piece, and here's why I put the x to the negative 1, it makes it easier to take my derivative. I could have left it a fraction, but fractions are hard to do derivatives with, especially with letters on the bottom. So minus 144 x to the negative 2. Now that I've done my derivative, let's flip that back so it's back to a fraction form because they're easier to work with. How do I work with this? I put one fraction on one side, and I put the other fraction over 1 on the other side. How can I solve that? Well, this is cross multiplying, right? I got 120x squared equals 144,000. Divide both sides by 120. So 144,000 divided by 120 gives me 1,200. And to get x, well, I just square root that. So my minimum happens when I get an x value of 34.64. And the question asked us, what dimensions? So I got the x dimension, how long the shed should be. How wide should it be? Remember way back here up at the top, we said y should be 600 over x. Let's use that. Y should be 600 over x. Or in other words, 600 over 34.64. What do we get for that? We get 17.32. The shed, here's our answer part A, cost is minimized by a shed with dimensions of 34.64 by 17.32. Here's part A. What's part B asking us? What is actual cost? Well, I have an expression for cost. Actually, a few expressions for cost. All of these are cost. So I'm going to pick one of them. I think I'm going to use the one right here. Okay, my cost is, just going to rewrite down at the bottom here, or B. My cost with relation to x was given by 120x plus 144,000 x to the negative 1, which we know is just like saying that. What's x? The x that minimized was when x was 34.64. So if I put that in for x in both spots, I can figure out my cost at 34.64 is, punch it all into your calculator. If you did it right, you should get approximately $8,304. Okay? Now these are the kind of questions we did back in grade 10 when we did quadratics. Obviously, we've done slightly more complicated versions of them now because we're using calculus, but some of the same ideas still exist. Okay, let's try one more of these quadratic kind of shapes. Something maybe you've seen before. Rectangular garden is being built next to a house. Okay, I need a house. Here's my house. And my garden is going to go next to it. I need a garden. Here's my garden. I don't know if it's along the house or not. It doesn't really make a difference. But it does say that the amount of edging needed if only 3 sides need to be framed. So in other words, I've got a side here, a side here, and a side there. The wall acts as my 3rd side. The area must be 60 meters squared. Well, this looks suspiciously like the last one. I can make an expression for area, which in our case is 16 equals x times y, which means I can probably rearrange this for one of my variables. Just thinking ahead, that's what I did last time. What else did they ask us for? They want to minimize the edging. How much edging do I need? Well, my edging is made up of 2 x's and a y. And I want to minimize that edging. So I want to write an expression for edging. And hey, I can use this in here. And now I've got an expression for edging in terms of x. If I want to minimize my edging, what can I do? Take a derivative, make it equal 0. So let's do that. Now, derivative of 2x is just 2. Just thinking here, okay guys, 16 over x is the same thing as saying 16x to the negative 1. Always, always, always. So really it's minus 16x to the negative 2 when I take my derivative, right? Using our process from last time, I can put 16 over x squared on one side, 2 on the other. I'll get 16 equals 2x squared. Divide both sides by 2, I get 8. Square root of 8 comes out to, we'll use our decimal version here, 2.83. There's my x. What did we say y was? We said y was 16 over x, right? So 16 over 2.83 comes out to 5.66. So to minimize edging, if x is 2.83 and y is 5.66. Your length and your width. Okay, those are sort of our basic grade 10 type questions. Let's move to a more advanced idea, if you will, and a grade 12 idea. I want to find the shortest distance between 2 moving objects. Okay. When I have 2 objects, maybe one's here and one's here, they're a certain distance apart to start. Well, if one object starts moving down, another one moves towards it, they are getting possibly closer than when they started. The distance from here to there might be less than it was initially. Okay, so our objective in this next series of questions is to figure out what's happening between two moving objects. Now to make it a little bit easier, all our objects are going to move in the cardinal direction, so north, east, south, west, or left, right, up, down. Just to make it a little bit easier, we're not going to be moving on angles at each other so much. That's going to allow us to use a Pythagorean relationship between the sides of our triangles. So I'll try the first one and you guys try the second one. The ship is sailing north at 9 kilometers an hour and observes a second ship 15 kilometers ahead. So I've got a ship down here. It's going this way. And it sees another ship. Right now, it's 15 kilometers ahead of it. Okay. The second ship is sailing east. So it's going this way at 12 kilometers an hour. What's the closest distance between the ships? So the big idea I have to think about here is my relationship between distance, speed, and time. And back to like science, we know our distance always equals speed times time. I put that in the wrong spot there. Hang on a second. Fix that. Sorry, guys. My distance equals my speed times time. So if I'm looking for the closest distance between things, and I know something about their speeds and their times, I can actually find a relationship between two things. Let's look at ship number 1. How fast is ship number 1 moving? It's moving at 9 kilometers an hour, but I don't know how long it's moving for. All I know is that my distance equals my speed times my time. It's moving at 9 kilometers an hour for a certain amount of time. So I'm hoping you guys would agree that this line is moving at a speed of, oops, not d, moving at a speed of 9t. And similarly, the second ship is moving east at, well, it's moving at a speed of 12t. At some point, these ships are hopefully going to be less than 15 kilometers apart. It would kind of be a silly question if they start off at 15. That's as close as they got, right? But we don't know where. So we're going to pick a random spot, theoretical spot, and say maybe they're closest when ship 1 gets here and ship 2 is over there. Maybe this is my minimum distance. Now again, those are theoretical spots. Maybe the actual distance should have been down here compared to here. I don't know. We're just picking a spot at random just for the idea of our diagram, okay? Not for the actual mathematical answer. Well, okay. So the distance that's covered here to here is 12t. This is d. How much is this? The 3 sides of my triangle. Well, it's not 15 kilometers. The whole thing is 15 kilometers, right? From here all the way down. It's not 9t. This is 9t. That's how fast it's going. The distance that's left between where it is here and the end is actually 15 minus 9t. The 15 kilometers we started at, and it's going to get smaller and smaller and smaller as the ship gets closer at a speed of 9 kilometers an hour. Okay, so I'm hoping that you can see that there's a right angle triangle in here. And I've got 3 sides that are related to one another. Okay, the 3 sides that are related are, let's write them down here for a second. It's green. D squared equals 12t squared plus 15 minus 9t squared. In other words, Pythagoras, a squared plus b squared equals c squared. Okay, now I want to minimize d. I want to find the closest distance. Hey, I want to take derivatives. I want to figure out my relation of d in terms of t, not d squared. So really, I need to take the square root of all this stuff. And then I need to solve this. I need to figure out where my derivative is 0. I want to minimize it. Okay, so here's our big idea. How do I solve this? Well, let's make this easier first of all. Before I solve my derivative, let's move this part down here. Let's make our function easier to work with. So what can I do? Well, root signs. I don't like root signs. Let's put a big giant bracket around it and put it to the power of a half. Make our life a little bit easier. 12t squared, I can do something with that. I can make it into 144t squared. And the 15 minus 9t, well, that really means 15 minus 9t times 15 minus 9t, right? So I can simplify this a little bit. Let's do some FOIL. 15 times 15 is 225. 15 times 9 is 135t. Inside 135t. 81t squared. So I move this bracket over here a little bit, sorry. All the power of 1/2. Make it a little bit easier still. Let's collect some like terms and put in the right order too. So I got 81, oh no, not 81. We got 81 plus 144. So we've got 225 t squareds. We've got the 270 t's and the number 225 all to the 1/2. Okay, so we took the idea of Pythagoras, we simplified it, we collected some like terms. Now we've got a form that's going to make it easier to take our derivative. Let's do that. So, power rule. This thing has to come down in front, right? So 1/2 times. The whole bracket stays the same, but we have to subtract 1 from our exponents. So we end up with negative 1/2 times the derivative of the inside piece. So we need to do 2 times this, which is 450t minus 270. Now that's a pretty messy looking expression, so let's simplify it. Let's think about, there's actually a fraction involved here. There's a 2 on the bottom, and because I have a negative exponent, all of this stuff actually fits on the bottom under a root sign, right? The root of a half. Sorry, the exponent of a half. So I can put that on the bottom. The last piece, there's no negative exponent on that piece, it's on the top. Now why would you want to do that, you might ask? Well, let's look at what we have now. We've got a fraction equaling 0. Well, can we cross multiply? 0 times all of this stuff is going to make 0. That makes things a lot easier. I'm left with 450t minus 270. Hey, I can solve that. 270 equals 450t. Divide both sides by 450. We get an answer of t equals 0.6. They're closest after 0.6 hours. Now, what does the question ask us? What is the closest? How do I find the closest? Remember when we started, we had this expression for d, right? We had all these expressions for d, actually. Any one of these ones right here will work. I'm gonna pick the top one this time. So I'm gonna take this expression. So my distance for t in relation to t is the square root of, it was 12 times t, which was 0.6 squared, plus 15 minus 9 times t squared. I'm going to take the square root of all that. So it's kind of a messy looking thing here, but what's that going to give us? The square root of 7.2 squared plus, if we do the part in the brackets, 9.6 squared, which gives the square root of all that. It comes out to 12. The closest point of approach, the closest they get, is 12 kilometers, which is closer than they were when they started. They were 15 to start. Okay, that's how we can do sort of a trickier, more in-depth kind of question involving time. Okay, I got one for you to try, so let's try pausing it, see if you can figure it out, and then we'll see if we can work on this together. So a plane flying east at 300 kilometers an hour passes an airport 10 minutes before a second plane flying south passes the same point. So here's my point, here's my airport. Okay, the plane's flying east, went past the airport. Okay. When the first plane was at the airport, the other plane was up here somewhere, right? It hasn't got to the airport yet. It was going this way. It was going south, but it wasn't there yet. Assume both planes are at the same altitude, just to make our life easier. They're not three-dimensional problem here, just two dimensions. When's the distance between them the shortest? So, assuming that plane 1 is flying south, or sorry, plane 2 is flying south, eventually it's going to reach a point where hopefully this is closer. Okay, what do we know about these planes? Plane 1 was flying at 300 kilometers an hour. So the distance it's covering, and our whole objective here is distance. Distance equals speed times time. 300 kilometers an hour for X hours will give us 300 t. That's how far it's gone. The other plane starts right here at this point is going 420 t. What's the difference this time? Last time I didn't give you the starting distance apart. We kind of need to figure that out. We need to know how far away from the airport the plane was when we started. We can figure out how far apart they are by using the idea again of distance, speed, and time. We know that the plane that's flying south takes 10 minutes to get to the airport. Well, how far is it going to go in 10 minutes? It's traveling at a speed of 420 kilometers an hour for how much of an hour? 10 minutes of the 60 minutes, right? 1/6 of an hour. So it's going to cover a distance of 70 kilometers. That's how far apart these planes are initially. Okay, so the distance here will be 70 minus 420 t. After that, it becomes the same question we just did a second ago. So see if you can set it up. Do the whole derivative. The process is actually exactly the same, just different numbers this time. So our distance should be the square root of 300t squared plus 70 minus 420t squared, and it's the root sign. We're going to simplify this. So I'm going to make this into a bracket. 300t squared comes out to 90,000 t squared. And we're going to do our FOIL. We're going to write our bracket out twice. I'm going to skip the showing of that part, but we're doing that times itself, right? Okay, so what will it give us? So 70 times 70 is 4,900. 70 times 420, and then 70 times 420 again. If we collect them, we'll get 58,800. And 420 squared gives us 176,400 t squared. And our exponent's a half now because I got rid of the root sign. If we collect that, we end up with 266,400 t squared minus 58,800 t plus 4,900 to the power of 1/2. There's our distance with respect to time. I want to take my derivative now. I want to set it equal to 0 because I want to know when do I minimize my distance. So, same thing we did before. Half comes down in front. Okay, our bracket stays exactly the same. So 266,400 t squared minus 58,800 t plus 4,900. Now to the negative 1/2. Derivative of the inside piece, really small here, 532,800 t minus 58,800. Okay, let's write the fraction form to make our life easier so we can cross multiply. On the bottom, we have the 2, the root sign, 266,400 t squared, 58,800 t, and 4,900. On the top, another bracket. Okay, we know we can cross multiply this and solve. The whole bottom is going to disappear. So we'll end up with 532,800 t minus 58,800. We're going to solve that. Same steps we did last time, just bigger numbers here. Okay, we're going to divide both sides by 532,800, and t will come out to 0.11 if you do it right. Okay, so the question was, did it ask us distance this time or time? It asked when is the distance, not what is the distance. So the shortest distance occurs after 0.11 hours. Okay, and that's the end of our simpler optimization problems. I know the last two weren't all that simple, but they are the same process, so it makes them a little bit easier to work with.